Hello everyone. The Laplace transform is having so many beautiful applications, and one of the best application of the Laplace transform is this transform can be used to solve differential equations. Not all differential equations, but definitely we can solve linear differential equations by using the Laplace transform. But the differential equations are having derivatives, and when we apply Laplace transform, then we have to find Laplace transform of the derivative. So how we can find the Laplace transform of derivative? Therefore, today in this video, we are going to see very important theorem, and that is derivative theorem of the Laplace transform. Now let us have the statement of this theorem. The statement of the theorem is if f is a continuous function on the open interval 0 to infinity and it is of exponential order alpha, and that the derivative of f denoted by f dash is a piecewise continuous function on the interval 0 to infinity, then show that Laplace transform of the derivative of the function, that is f dash t, is equal to s times Laplace transform of f of t minus the value of the original function at t equal to 0, that means f of 0, and this result is valid for real part of s greater than not 0, it is alpha, because our function is of exponential order alpha. So now this important theorem we are going to prove. So if we read this theorem carefully, at the inception it is written f is continuous function on 0 to infinity. So this implies the piecewise continuity of f, and this function is of exponential order alpha, and therefore by using these two conditions of small f function, this condition will give us the guarantee of existence of Laplace transform of this function. So you may write since f is a continuous and it is of exponential order alpha, therefore you can write Laplace transform of f of t exists. It may be denoted by capital Fs, but it is exist. Now we have to show that this result. Now how we can prove that? So here we have written Laplace transform of f of t exists, and we know that the function f is of exponential order alpha. So you can write here since f is of exponential order alpha, what is its meaning? Meaning is therefore there exists a constant which is denoted by capital M such that mod of this function f of t is less than or equal to this constant capital M into e to the power alpha t, and this is true for all t greater than or equal to 0. So this is the definition of exponential order alpha, and we can use this fact to prove the existence of the integration later on. So keep in mind this fact. Okay. Now we want to show that this result, so we are starting with LHS, and LHS is Laplace transform of f dash t. F dash means it is a derivative of f with respect to t. Now according to definition of Laplace transform, we know it's a definition in terms of integration, that is 0 to infinite e to the power minus st into this function f dash t dt. Now in this integration, it is a product of two functions. One is a kernel, that is an exponential function, and another is f dash t, that is a derivative of f. So to solve this integration, we have to use integration by parts. So that's why I'm using integration by part. And what is that integration by part? You draw two empty brackets first, then minus, again integration with limits 0 to infinite, again two brackets, and it is dt. So this is outline of by part. Now the only work remaining is that to fill the brackets. In first bracket, I can write first function, that is e to the power minus st. In second bracket, I am writing integration of second function, that means integration of f dash t with respect to t. So since dash means derivative with respect to t, and I am taking its integration with respect to t, therefore integration and derivative get cancelled. Therefore, I am getting here f of t. Keep in mind, this f of t is nothing but an integration of the second function. Now, since it is improper integration, therefore I am giving the limits from 0 to infinite. And later on, we can calculate the value of these two brackets. Now the next target is how to fill up these two brackets. Now to fill these two brackets, we are using these two brackets. Now here, whatever the first bracket, you take the derivative of this quantity with respect to t and write in the first bracket. So here it is exponential function, therefore its a derivative with respect to t is e to the power minus st into, again derivative of minus st, that is minus s. And this quantity you are keeping as it is here, therefore here I am writing only f of t. Alright. Now I am putting these upper limits and lower limits, but we will calculate this value later on. So I am keeping as it is. So it is e to the power minus st into f of t, and its limits are from 0 to infinity. Now see what happened here in the second term. This is minus s. We are taking integration with respect to t. Therefore, minus s is independent for this integration. And therefore, this independent quantity we can take outside the integration. So when minus s is coming out from the integration, then I will get this minus and this minus will become plus this s, and now integration from 0 to infinity e to the power minus st f of t and dt. Oh, now I am observing this integration. And what is this? This is original definition of Laplace transform of this function. So therefore, instead of this integration, I can write Laplace transform of f of t. So therefore, in the next step, I can write first two brackets keeping as it is, e to the power minus st. Second bracket is f of t, and its limits are from 0 to infinite. This is plus s into, according to definition of Laplace transform, that integration is equivalent to this quantity, Laplace transform of f of t. Now only work remaining is that evaluate the value of these two products, these two brackets. Okay, so now how I can solve this? So first of all, I will take a limit as t tends to infinity, because I am calculating for upper limit, and this is e to the power minus st ft. All right, minus the lower limit is 0, therefore I am writing t tends to 0, and again the quantity is e to the power minus st f of t, and the last quantity I am keeping as it is, s into Laplace transform of ft. Okay, now what should be the answer of this limit? When I put t equal to infinity here, how I will get the value of this function is 0, because for getting 0, when we put infinity, s must be positive, and therefore what I am considering here, consider s is a complex number, therefore that complex number can I write like this, x plus iy. And now I am considering the whole product and its absolute value, e to the power minus value of x is, s is x plus iy into t f of t, and it is equal to, or yes, it is equal to mod of e to the power minus xt plus iyt. You can give separate mod to this function because it is a multiplication, and mod of f of t. So this is a complex number, therefore its mod is nothing but e to the power minus xt. Alright, and the value of mod f of t already we have written here. You check here, see, this is the value of what? Mod f of t. Therefore we can write the value of this, but it is less than or equal to, therefore we can change this sign, and here this is m into e to the power alpha t. Now just simplify this, it is m into e to the power, we can take minus as a common, x minus alpha into t. This is a very simple calculation, base is same and therefore multiplication, therefore we can add the indices, and after adding the indices you can take minus as a common and t is also common. But you know that this is s x plus iy, and here the real part of s is x, and that x is here, therefore we can write real part of s instead of x here. But to get this, now I am putting this value here, or I can take the limit. So limit as t tends to infinity of this e to the power minus st f of t is less than or equal to limit as t tends to infinity m e to the power minus x minus alpha into t. And to get the answer of this limit as a 0, the condition is that this bracket must be positive. So this is this limit is equal to 0 when this bracketed quantity, that means x minus alpha, is positive. So that's why it is equal to 0 when, what is x? X is nothing but real part of s greater than, you can transfer this alpha to right hand side. Therefore, this value is equal to 0 for real part of s greater than alpha. Therefore, here now I can consider this first term, value of the first term is 0 for this condition. And when you put t equal to 0 here, it will become 1 and it is f of 0, right? So if we call this expression is an equation number 1, and in this equation 1, for the first term, if I consider these calculations, then first term, value of first term will become 0 for this condition. Therefore, I can write from equation 1, for real part of s greater than alpha, equation 1 becomes, this is left hand side is Laplace transform of f dash t, and it is equal to, the first term will become 0 minus this is f of 0 plus s into Laplace transform of f of t. All right, so this is a positive term, therefore we can write at the first position, therefore it is s into Laplace transform of ft minus f of 0. And see, this is what we want to prove. Laplace transform of f dash t is equal to parameter s into Laplace transform of original function f of t minus the value of the function at t equal to 0. Keep in mind, in this theorem, this is the original function and this is a derivative of that original function. So for the existence of the left hand side, this f dash t must be only piecewise continuous. There is no need to have this f dash t as an exponential order function. And this is the beauty of this theorem. This is the very remarkable thing that we are studying here, that to get the Laplace transform of f dash t, this f dash t must be only piecewise continuous function. There is not necessary to have this f dash t as a exponential order. We can give the counter example also, right? So what is the counter example? If you take this is the counter example for your understanding. Counter example, let us consider a function ft is equal to sine of e to the power t square. Okay, now its derivative is cos e to the power t square into e to the power t square into derivative of t square is 2t. So this is f dash t, and this is trigonometry, therefore it is continuous function. It is exponential, so it is also continuous function. This is the polynomial, it is also continuous, and product of three continuous functions is again a continuous. So this function is only continuous function, but this function is not exponential order, and still we can find the Laplace transform of f dash t by using this result, and that's why this result is very important. So after this result, we can use this statement to solve or to find the Laplace transform of derivative of any function, and this theorem will make easy to solve linear differential equations. Now the question arises, here we have found Laplace transform of first derivative of f. What will happen when we are finding Laplace transform of second derivative of f? So this is a very interesting thing, and we are going to prove what will be happen when we are finding Laplace transform of f double dash t. So it is a double derivative. So how to find this? So it's very simple, not necessary to write all the terms which we have calculated earlier. The only thing is, let you suppose g of t, another function, as f dash t, okay, and therefore g dash t is equal to f double dash t. Now I want to find the Laplace transform of f double dash t. It is equivalent to Laplace transform of g dash t, because both are equal. And we know that how to get the Laplace transform of first derivative. How we can write? You write first s, then Laplace transform of original function. Here derivative is taken of g, so here g is original function, so I am writing g of t is the original function, take its Laplace transform, minus value of that original function at t equal to 0. This we have written due to the previous result. Alright, this is s into. Now again this s keeping as it is, Laplace transform of g of t, but already you have mentioned here g of t is nothing but f dash t. So I am putting the value of g of t, and it is f dash t, okay, minus g of 0. Now again this is a Laplace transform of single derivative of f. Here it was g, here it is f. So it is s into, again use the derivative theorem here for f. So here original function is f, its derivative is f dash, and we are calculating the Laplace transform of f dash. Therefore we can write this as a s into Laplace transform of original function, that is ft, minus value of that f at t equal to 0. Keep this bracket complete, and this g of 0 as it is. Now after simplification, this s into s will become s square, Laplace transform of ft, and now this s multiplied to this f of 0 also, so minus s f of 0 minus g of 0. So here g of t is equal to f dash t. Then tell me what is the value of g of 0. Put t equal to 0 in both sides. I will get g of 0 is equal to f dash 0. Therefore I am writing here f dash 0. So this is the answer of Laplace transform of f double dash t. So from these two results, I have observed that whatever the order of derivative of f, that order is nothing but the index or exponent of s in the first term of required answer. And therefore in general, we can write this result for nth derivative, Laplace transform of nth derivative of f is equal to, you write s first, the order of the derivative is n, therefore the index power of s must be n. Now into Laplace transform of original function, that is ft. Now here is the square, and after this term, in next term the power should be reduced by 1. So minus I can write reduced power of s, that is s raised to n minus 1 and here I am writing f of 0, then again minus, again reduce the power of s and minus 2, and here I can write f dash of 0, now again minus s raised to n minus 3, f double dash of 0. In this way, you just complete all the terms. In each term, the power of s is decreasing by 1 and derivative of f is increasing by 1. All right. So in this fashion, dot dot dot, the last term should be, this is minus, the last term should be, see here the order is 2, therefore last term is having order 1. So whatever the order of this, the last term should have order less than 1. So here the order of derivative, order of this function is n, therefore here the last term is having order less than 1 at t equal to 0. So this is the general result, and using this result we can find the Laplace transform of any derivative of f. All right. Now after this result, now I am very much curious about what will happen, because in this result we have calculated Laplace transform of derivative. So instead of derivative, if I write integration, so what will be the answer? So it's very interesting that what will be the Laplace transform of integration. So therefore we will see next result, that is how to find Laplace transform of integration. So Laplace transform of the integral, and let's have statement. If Laplace transform of f of t is equal to fs, then Laplace transform of integral 0 to t fu du is equal to fs upon s. Fs upon s, it means that Laplace transform of the original function, here it is u, this is dummy index, because your upper limit is t, therefore there is not an issue about the variables. You can use any variable, so I am using t. This is the Laplace transform of f of t. It is denoted by f of s divided by s. So the first impression of this theorem is that while I was calculating Laplace transform of derivative, there is a multiplication of s to the fs, and here we are calculating Laplace transform of integral, and see the behavior of s in integral. The s is not multiplying, s is dividing. Okay, all right. So definitely this is true for a real part of s greater than 0, right? That condition is required. Now the question is how to prove this, right? So what I'm doing here, this is an integral, okay? So to prove this result, that integral, I'm writing here that 0 to t small f u du. See, this is a function with variable u, and I'm finding its integration with respect to u, and after that I'm putting upper limit as a t and lower limit as a constant 0. Therefore, whatever the answer I will get after this integration, that should be again a function of t. So therefore here I am considering that function by g, and it is a function of t. And let me call this expression is an equation number 1. All right. Now I will calculate two things. One is what should be the value of g of 0. So just I am putting t equal to 0. So right hand side will become integral from 0 to 0 f of u du. And we know that in definite integration, when the upper limit and lower limits are same, then the value of the integration is 0. So this is my equation number 2. Now this is a function of t, therefore I can find the derivative. So differentiate equation 1 with respect to t. So in the left hand side, it is a function of only single variable, therefore I can use ordinary derivative d by dt of g of t, and the standard notation is g dash t. We can write this as a g dash t. But here the problem is in the right hand side I am observing two variables. One is t as well as u. And therefore, I have to take partial derivative with respect to t of the right hand side. 0 to t f of u du. Keep in mind, our integration is with respect to u, and we are taking integration with respect to t. Therefore, integration and derivative will not be cancelled. Right? So, we are using derivative under integral sign. And how we can write this as you keep this integral as it is, 0 to t dou by dou t, this operator take inside the integral sign, this is f of u du. The next term is plus, you write this integrand putting the upper limit in place of u, that is f of t, and then take the derivative of that upper limit with respect to t. Minus, again you write this function by putting u equal to lower limit. So I can write this as f of 0 into d by dt of that lower limit, that is 0. This is a rule of derivative or differentiation under integral sign. Now look at this integrand. This is a function of u, and you are taking derivative with respect to t. T is not present at all here. Therefore, the derivative of this quantity is 0. Therefore, the value of first term is 0 plus ft as it is, and the derivative of t is 1. So, it is not necessary to write 1 here. Minus derivative of 0 is 0. Therefore, I am getting the value of g dash t is equal to what? F of t. And let me call this expression is equation number 3. I want to use 1, 2, 3, all the 3 equations to get my answer. Alright. Okay. Now, I want to calculate, or I want to prove this result. So I will start with left hand side. So Laplace transform of integral 0 to t f of u du, right? And that integral is nothing but g of t. So start with this Laplace transform of integral 0 to t f of u du. It is equal to what we can write? We can write as a Laplace transform of g of t, because already we have assumed that this integral is g of t. Okay. Now use the definition of Laplace transform, that is integral from 0 to infinite. Kernel of the Laplace transform is e to the power minus st multiplied by that function gt dt. All right. Now I want to solve this integration, and I know that this is a product of two functions, and therefore I want to use integration by part here. But To use the integration by part, I have to rearrange this integration like this. You take first function of this product as a g of t, and second function is the exponential function. Keep in mind this step. This is a very important step. Now I am performing, or I am calculating the value of this integration by using integration by part. So what is the way to get the value of integration by using by part? First, draw two empty brackets minus integration from 0 to infinity, again two empty brackets with respect to t. Now you fill the first empty bracket by using this. You keep this function as it is, g of t. Now here you have to find the integration of this function and then put in second bracket. So after integration with respect to t, it is e to the power minus st, not integration. Yes, it is integration, st divided by derivative of this with respect to time, that is minus s. So I am putting here. All right. Now the time is to fill these two brackets. Now this first function, take its derivative and put here. Take the derivative. So the derivative of g of t is g dash t. And this bracketed quantity keep as it is here, minus st divided by minus s. And here I am giving the limits from 0 to infinite. All right. Okay. So for real part of s greater than 0, I'm restricting this value for this condition only, because now I am putting t equal to infinity here, and to get the value of this exponential at t equal to infinity as a 0, we must need that s or its real part greater than 0. So since we have restricted with this condition, therefore when we put upper limit here, this will become 0. So the upper limit is 0 minus, put the lower limit, so you can get g of 0, and when you put here 0, then you will get e to the power 0 1 upon minus s. So this is the answer of first term. And now this minus will get plus, integration from 0 to infinite, that s also we can write this as a 1 by s. Okay, 1 by s here, e to the power minus st, and here we can write g dash t. Okay. Now from equation 2, see what I want to write the value of g of 0. See the equation number 2, the g of 0 is 0. Therefore this term is also become 0. So it is 0 minus 0 plus 1 upon s, integral from 0 to infinite, e to the power minus st, and this is the kernel of Laplace transform, g dash t dt. So look at this integration. This is the very clear-cut definition of Laplace transform. But here the function on which we are acting this kernel, that is g dash t. Therefore the value of this integration is nothing but Laplace transform. So I can write 1 by s into Laplace transform of this function g dash t. G dash t. And Can you know the value of g dash t from equation 3? Look at here. G dash t is equal to what? F of t. So I can replace, this is 1 by s Laplace transform of f of t. Instead of g dash t, I can replace by ft. And the Laplace transform of f of t is denoted by fs. It is given actually, divided by s. See, we have started with this side, and after simplification I will get this side. Therefore, the Laplace transform of this quantity, this integral, is equal to fs upon s. So finally I can write, therefore Laplace transform of integral 0 to t fu du is equal to fs upon s. And this is the final result which we have proved. So I can give the bracket to this result. So this is the final result. Okay, so this is the end of this lecture. We will see some other properties of Laplace transform, and then we will solve more and more examples of Laplace transform by using these all properties which we have studied in the previous lectures. तब तक के लिए बाय बाय.